Hello, thank you for attending my presentation. My name is Gözde Özcan, and I'm a third-year PhD student at the ECE department of Northeastern University. Today, I'll present our paper titled Submodular Maximization via Taylor series approximation. In this paper, we focus on maximizing submodular functions. Submodular functions are set functions that exhibit diminishing gains property. Their maximization is a topic with theoretical consequences and far-reaching applications. Submodular maximization problems naturally arise in facility location, document summarization, influence maximization, and maximum coverage problems, to name a few. Let's take a closer look at the maximum coverage problem as a concrete submodular maximization example. Given a finite ground set V of locations and the subset S of V, set function f is the number of locations covered by adding sensors to the locations in S. In this example, when S contains S1, S2, and S3, f of S is 73. This exhibits diminishing returns property, meaning the marginal gain of adding a sensor to a smaller set is larger than the marginal gain of adding the same sensor to a larger set. For example, the marginal gain of adding S3 to empty set is larger than adding it to the set of S1 and S2. Submodular maximization problems can have different constraints. For example, in the same coverage problem, limiting the total number of sensors we can place by an integer k would be an example of a maximum coverage problem subject to a cardinality constraint. This can be expressed formally as follows. Another instance of constraints are matroid constraints. The formal definition of matroids will be given later. For now, I'll just give an example of a matroid constraint. In the same coverage problem, dividing the ground set into disjoint sets, where each set has its own cardinality constraints, would be a maximum coverage problem with a matroid constraint, which can be formally expressed as follows. Even though this type of problems are NP hard in general, polynomial time approximation algorithms exist. One such approximation algorithm is the famous greedy algorithm. It successfully achieves the 1 minus 1 over e approximation ratio on uniform matroids. However, this approximation ratio drops down to 1 over 2 for partition matroids. The continuous greedy algorithm improves this ratio on general matroids and achieves the optimal 1 minus 1 over e ratio. Continuous greedy algorithm requires computing the multilinear relaxation of a submodular function f. Formal definition of the multilinear relaxation is as follows. Multilinear relaxation of f is the expectation of f assuming each subset S of V is randomly sampled according to an independent Bernoulli trial. In other words, for every element I in V, probability of I belongs to set S is by I, whereby I is between 0 and 1. This causes a certain drawback. In particular, computing the multilinear relaxation requires a summation over exponential number of terms. Current methods often rely on sampling in order to compute this in polynomial time. However, computing the multilinear relaxation with sampling can be still expensive, considering the number of samples required can go up to the 8th power of the size of the ground set in some cases. However, this is not always the case. There are problems for which the multilinear relaxation is easy to compute. For example, when f is the coverage function, multilinear relaxation of f has a closed form. Therefore, it does not require sampling. The reason why this happens is that the coverage function is a multilinear function. Moreover, this holds for all multilinear functions, meaning their multilinear relaxation has a closed form and they don't require sampling. In this paper, we extend this notion of multilinearity to the functions which can be formalized as compositions of multilinear functions. And we show that for this type of functions, multilinear relaxation of f still has a closed form. Hence, it does not require sampling. We do so by first taking the Taylor approximation of the function h. This results in a multilinear estimator f hat. Second, we use this estimator instead of f and take its multilinear relaxation. This result ends up having a closed form and hence does not require sampling. Our contributions can be summarized as follows. We propose a novel polynomial estimator for approximating the multilinear relaxation of submodular functions in a certain form. we provide theoretical guarantees for a variant of the continuous greedy algorithm that uses our polynomial estimator. We show that multiple applications such as data summarization, influence maximization, can be cast as examples to our framework. We conduct experiments for multiple problem instances on both synthetic and real data sets. We observe that our estimator achieves 74% lower error in 89% less time in comparison to the sampling estimator. Before introducing our polynomial estimator, I want to give some background information. Throughout the paper, we are working with monotone and submodular functions. A function f is submodular if for every A subset B subset V and E belongs to the set difference of V from B, it holds that marginal gain of adding element E to set B is less than or equal to the marginal gain of adding the same element to set A. Additionally, a function f is monotone if for every A subset B subset V, f of A is less than or equal to f of B. Given a ground set V, a matroid is a pair M with V and I, where I is a collection of independent sets for which the following holds. If B belongs to I and A is a subset of B, then A also belongs to I. If A and B both belongs to I and the size of A is less than the size of B, there exists an X in the set difference of B from A such that A union X belongs to I. On the right, we see the example of a partition matroid we discussed before. There is a one-to-one correspondence between a binary vector x whose coordinates are either 0 or 1 and its support S. Therefore, the set function f of s can be interpreted as f of x. We will use this convention for the remainder of the presentation. As an example, the coverage function f can be formalized as follows, where L represent the possible locations in V and Ji represent the set of locations covered by each sensor I. The continuous greedy algorithm operates as follows. Instead of directly maximizing a submodular function, the continuous greedy algorithm handles its multilinear relaxation in the continuous domain. Proceeding in iterations, it maximizes g of y, where y belongs to the matroid polytope P of M, characterized by the matroid M, and produces an approximate fractional solution y star. Then, this fractional solution is rounded back to the integral domain. For continuous greedy algorithm to work, multilinear relaxation of f needs to be computed. A function is called multilinear if it is affine with respect to each of its coordinates. Equivalently, multilinear functions are polynomial functions in which the degree of each variable in a monomial is at most 1. We are interested in multilinear functions because their multilinear relaxation evaluated over independent Bernoulli coordinates has a closed form. Therefore, they can be estimated without sampling. We exploit this powerful property of multilinearity on a broader array of functions. Given a multilinear function g, we approximate arbitrary analytic functions of g using Taylor series. By doing so, we leverage from the observation that when restricted to binary values, polynomials of multilinear functions are still multilinear. Exploiting this, we approximate the multilinear relaxation of an analytic function via Taylor series. The resulting approximation is called the nth degree polynomial estimator of f. Moreover, this estimator is multilinear and therefore directly computable without sampling. We make the following two assumptions on f. First, we assume that the function f is monotone and submodular. Second, we assume that f has this form. This means that the function f can be expressed as weighted sum of analytic functions of g, where g is a multilinear function and there exists a polynomial f hat of degree L. Now we can state the main theorem of our paper. Assume a function f satisfies the assumptions on the previous slide. Then consider the continuous greedy algorithm, in which g of y is estimated via the polynomial estimator f hat L. Then g of y is greater than or equal to 1 minus 1 over e times g of y star minus big O of epsilon L minus big O of 1 over k, where g is the multilinear relaxation of f, Y is the approximate solution generated by the continuous greedy algorithm. Y star is an optimal solution to the continuous maximization problem. Epsilon L is the bias of the estimator, and K is the number of iterations in the continuous greedy algorithm. In the paper, we showed that summarization, influence maximization, facility location, and cache networks can be cast as examples of our framework. Furthermore, we showed that for these examples, the bias of the polynomial estimator can be made arbitrarily small by increasing the order L. We execute the continuous greedy algorithm with sampling and polynomial estimators over different problem instances and graphs. Here, I'll show the results of one of our experiments. We conduct this experiment on a synthetic dataset for an influence maximization problem. We measure the performance of different estimators with an error metric we define as follows. In Figure 1, we plot the trajectory of this error as a function of time. Each line in this plot represents the trajectory of a different estimator. Dark and light blue lines represent polynomial estimators with degrees 1, 2. Orange, red, and pink lines represent the sampling estimators with the number of samples, 1, 10, and 100. In Figure 2, we are only interested in the error function of the end results of the continuous greedy algorithm as a function of time. Blue line represents the polynomial estimators, while orange line represents the sampling estimators. Both of these plots show that polynomial estimators outperform sampling estimators in terms of error. Moreover, polynomial estimator with degree 1 turns out to be the fastest estimator. In conclusion, we propose an alternative to the sampling estimator which is polynomial and achieves 1-1/(e) approximation ratio. In the future, this work might be extended to online and stochastic algorithms. Thank you so much for your time and attention. I'd be happy to answer your questions if you have any.